Welcome back to part 2 of surface integrals of a vector field. In part 1 we talked about if S is an oriented surface given by z equals g of x and y, and r is in the xy plane, based upon the orientation of the surface affects how we evaluate the surface integral as a double integral over the region R. Notice that the orientation is upward. We take the opposite of the partial derivatives of the g with respect to x and y, and the z component is positive 1. And if the orientation is downward, we take the partial of g with respect to x, the partial of g with respect to y, and then the z component would be negative 1. Let's go and take a look at our second example. We want to determine the flux across where the vector field is equal to angle bracket x, y, z across the surface above the xy plane with a unit normal vector oriented upward. So the first thing we should recognize is that g of x and y is equal to 9 minus x squared minus y squared. And again, before we set this up, let's go ahead and take a look at this graphically. Here's our surface in green and our vector field in red. So the value of our surface integral will represent the flow rate across this blue surface. And you can see from the graph, it looks like it will be upward in the same direction as our orientation, so this should give us a positive flow rate. So our surface integral is going to be equal to the double integral over the region R of this dot product. So for f, we're going to have x, y, and then for z, we're going to replace that with 9 minus x squared minus y squared. Everything needs to be in terms of x and y. We'll dot this with the opposite of the partial derivative of g with respect to x. Well, the partial derivative would be negative 2x, and the opposite of that would be positive 2x. And then for the partial derivative of g with respect to y, that would be negative 2y, and then we'll take the opposite of that, that'll be 2y, and the z component will be 1, differential a. Let's go ahead and find this dot product before we determine our variables of integration and our limits of integration. So we'll have 2x squared plus 2y squared. We'll have plus the quantity 9 minus x squared minus y squared. So we're going to have x squared plus y squared plus 9. Then before we decide our limits of integration, let's go and look at our xy trace. So if z is equal to 0, we would have x squared plus y squared equals 9. So we have a circle centered at the origin with a radius of 3. So I think what we'll do here for this one is use polar coordinates. Let's go do the conversion on the next page. Okay, so we're going to use polar coordinates. X squared plus y squared is equal to r squared, so we'll have r squared plus 9. And then differential a is going to give us an extra factor of r, dr, d theta. So r is going to be from 0 to 3 based upon our xy trace, and theta will be from 0 to 2 pi. So we're going to have r cubed plus 9r So we're going to have r to the fourth over 4 plus 9 halves r squared. Replacing r with 3. And then when r is 0, we'll have 0. Forgot the d theta here. To save a little bit of time, I've already worked this out. It comes out to 81 fourths plus 81 halves. That's 243 fourths. So I have 243 over 4 times 2 pi minus 0. That'll give us 243 pi over 2 as our flow rate across that surface. Remember, the surface had an upward orientation, and the flow rate was positive because it was in the same direction as our orientation. So the flow rate is up from the surface given this vector field. Okay, I hope you found this example helpful. Thank you for watching and have a good day.